Welcome to Episode 3, Scoping and Inheritance, Boundaries, Providers, and Proofs. In any security framework, scope is where control meets reality. If the scope is unclear, no amount of policy will hold together when tested. Defining what a system includes, what it connects to, and what it depends on determines every downstream decision. A program can fail not because controls were wrong, but because boundaries were guessed instead of defined. The NIST 853 process treats scoping as the foundation of credibility. Imagine a surveyor marking land before construction. The lines do not build the structure, but without them, the building cannot stand. A well-scoped system keeps accountability intact from the first planning document to the final audit. Building on that, defining the system's purpose and boundaries gives every control meaning. A boundary is the perimeter of responsibility around people, technology, and data. The clearer it is, the easier it becomes to test compliance and assign ownership. To define a boundary, start with the system's purpose, what it exists to do, and what it must protect to succeed. A payroll system, for instance, might include application servers, a database, and the secure network segment connecting them, but exclude the organization's public website. Drawing this line clarifies which risks belong to the system owner and which sit elsewhere. A boundary that is too wide wastes effort. One that is too narrow invites gaps. From there, identifying components, interfaces, and data flows turns the abstract boundary into something operational. Each piece of hardware, software, and connectivity path inside the boundary should be known. Interfaces mark where systems touch and where trust must be negotiated. Data flows show how information enters, moves, and leaves. For example, if the payroll application exports files to a finance platform, that interface defines a control point. Mapping these details helps prevent surprises later during testing or incident response. A clear diagram of components and flows makes complex systems manageable and keeps risk analysis anchored to facts, not assumptions. Next, distinguishing the authorization boundary from the environment of operation ensures that assessments stay focused. The authorization boundary is the official scope of the system being approved, while the environment of operation includes everything it depends on but does not control. A hosted application, for example, might have its code, databases, and encryption keys inside the authorization boundary, but rely on a cloud infrastructure belonging to the environment of operation. The distinction prevents assessors from chasing endless dependencies while ensuring that inherited controls from the environment are still verified. Without this separation, organizations either overextend effort or miss critical dependencies. As systems expand, understanding providers, services, and shared responsibilities becomes essential. Modern environments rarely live in isolation. Cloud vendors, managed service providers, and third-party platforms each bring their own controls and limitations. The shared responsibility model defines which party handles which safeguards. For instance, the provider may manage the physical security and hypervisor, while the customer manages identity, encryption, and configuration. Successful programs translate this division into written agreements and evidence paths. When everyone knows their share of the burden, audits become cooperative rather than adversarial. Ambiguity here, by contrast, is where most compliance failures begin. Building on that, inheritance defines what you take from another entity's assurance package and what you still must verify. Inheritance allows systems to rely on tested controls implemented elsewhere, such as network firewalls maintained by an enterprise operations team. However, inheritance is not blind trust. The receiving system must confirm that the provider's control is valid, operating, and covers the intended risk. For example, inheritance vulnerability management from a central IT team still requires proof that scans include your servers. Treating inheritance as verified dependency, not assumption, keeps accountability visible and defendable. With those relationships mapped, organizations must also define what is explicitly out of scope, supported by rationale. Out-of-scope elements are not ignored. They are acknowledged as external to assessment responsibility. A simple note like corporate email excluded, governed by enterprise communication system, prevents confusion later. Documenting why something is out of scope shows intent rather than omission. This precision helps auditors focus on what truly matters while shielding teams from being evaluated on areas they cannot control. Clear exclusions, stated early, are marks of disciplined engineering, not evasion. Many organizations also operate across multiple environments: development, test, and production, each with different controls and data sensitivity. Multi-environment scoping ensures that each stage receives appropriate treatment without overextending assessment boundaries. For instance, development environments may use synthetic data and lower authentication requirements, while production demands strict controls. If the same infrastructure hosts both, boundaries must separate them logically or physically. This differentiation helps ensure that weaknesses in one phase do not undermine another. Treating each environment as a related but distinct entity gives both developers and assessors clarity about risk containment. At the same time, boundaries depend heavily on identity, data, and network perimeters. The identity perimeter defines who can act within the system. The data perimeter defines what information is handled, and the network perimeter defines how traffic flows. Modern architectures blur these lines through remote work, cloud adoption, and APIs, so scoping must capture where those perimeters actually exist. Imagine a remote contractor accessing systems from a personal device. Without careful scoping, that access route might sit outside formal review. By naming every perimeter explicitly, organizations prevent invisible extensions of their boundary and keep defense coherent. Once scope is defined, documentation artifacts prove it. Key artifacts include system boundary diagrams, data flow charts, asset inventories, and responsibility matrices. These materials show how the team reasoned through inclusion and exclusion. For example, a diagram linking web servers, databases, and authentication services provides visual proof of scoping logic. During authorization, reviewers rely on these artifacts to confirm that stated boundaries align with implementation. Treat these documents as living references, updated when architecture changes. Their clarity signals program maturity more than any slogan could. Scope choices also shape how sampling works during assessments. Sampling means selecting representative evidence to verify control operation without testing every instance. A narrow scope with few components might allow full coverage, while a broad system requires sampling strategies. If a boundary includes multiple data centers or applications, samples must represent each context. Poorly scoped systems lead to weak samples, producing false confidence. Understanding how scope affects sampling helps balance efficiency with assurance. The art lies in choosing scope that is defensible yet testable within realistic resources. Despite best efforts, scope errors still occur and must be recognized early. Common mistakes include mislabeling inherited controls, forgetting shared interfaces, or allowing scope drift as new features launch. When discovered, remediations should focus on revisiting the original boundary statement and updating diagrams, records, and approvals. For example, if a new mobile app connects to the main system, that link must be formally added to scope. Correcting these errors is less about blame and more about restoring transparency. The sooner a scope gap is closed, the fewer surprises arise during authorization. Before final authorization, governance checkpoints confirm that scope, inheritance, and documentation align. Review boards often require the system owner, assessor, and authorizing official to agree on the boundary and inheritance map. These checkpoints serve as formal reality checks, catching inconsistencies before they spread into implementation or audits. They also establish accountability for future maintenance, defining who must approve boundary changes. Without governance validation, even the best scoped system risks unraveling under pressure. Structured checkpoints make sure scope decisions remain both accurate and owned. In the end, clear boundaries and credible inheritance form the backbone of a trustworthy security program. Every control depends on knowing where responsibility begins and ends. When teams define, document, and defend scope with precision, the rest of the framework falls naturally into place. Inheritance then becomes a strength rather than a vulnerability, linking systems through verified trust instead of assumption. The outcome is confidence. Confidence that when auditors ask, engineers can show exactly where the line lies, why it was drawn, and how it is maintained. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.